Just got through with that three-body problem. Now, what's the three-body problem we want to talk about? Well, the three-body problem that I want to talk about is helium. But when we study helium, there's some assumptions made that we know all about hydrogen. So let's start with hydrogen today. Hydrogen is a two-body problem. It has a nucleus and it has an electron. The nucleus is far more massive than the electron. So in this case, we're going to assume that the proton has infinite mass as compared to the electron. I think that's a pretty good assumption. That works mostly, because if we don't, then we have to account for the fact that the electron pulls at the proton and the proton pulls at the electron, and they both move. But we're going to assume that the proton doesn't care about the electron and the electron is just super attracted to it. Kind of like a human and Earth. Earth is so much more massive, you never consider that when you're doing the gravitational force. Let's quickly, and I mean quickly, dive into the calculations. Here's where we're going to start. We're going to derive the hydrogen electron energy levels. Hydrogen electron energy levels will tell us a lot about not only the energy, but it will also tell us the position of the electron, so we can actually look at what the orbital is and at least verify it with the math. Next, we're going to discuss the time-independent Schrödinger equation. This right here is the Schrödinger equation. And it says that the H, which is the Hamiltonian, and the little hat means operator, if we take this and operate on the state function, and the state function gives us all of the possible things we can measure, like energy, but also like position. And all of this is in a multi-dimensional space, which we won't dwell on that now. And then over here we have an E, which doesn't have a hat on it, and that same state function over here. The E is the values that we return from this. And in this case, we're concerned about the energy values. So if I take the state function, operate on it with this thing, this Hamiltonian, then we get the energies. Hamiltonian is the expression of the energy. Here's the energy values that we're going to come up with. Now let's break out the Hamiltonian. The Hamiltonian is mass. We know what the mass is. H bar. H bar, it's got a little mark through the top of the H there, and that stands for Planck's constant over 2 pi. Now, Planck's constant that's quantum. That's the whole thing about quantum mechanics, about quantum chemistry, is that things are based in little steps or quanta. Then this thing, upside down triangle, is the Laplacian, and what the Laplacian does is take here's that number 2 out there, it takes the second derivative, second partial derivative, because we're taking it with respect to x, with respect to y, with respect to z, and that is what we operate on the state function with. Then out here we have this thing. This represents the kinetic energy term, and this represents the potential energy. This is the Coulomb type law form, and this is 4 pi times e to the 0. Now this epsilon is actually the permittivity. This is the constant that associates the units so that it comes out correctly as a potential energy. And this R is the distance from the center of our coordinate system. Rather than x, y, and z, we're using an R here, which will change the Laplacian from with respect to x, y, and z. It'll be with respect to spherical coordinates, those that are based on a center and a radius at different angles. Magnitude of the radius and two angles gives us any point in space. Then we have E, that's the electron charge. Now, why are there two of them? Why is it E squared? Why E times E? Well, the charge on the proton is plus, the charge on the electron is minus, so it's E squared, and this gives us an attractive potential rather than a repelling potential. Here I warned you, here down here are the spherical coordinates. A radius, a theta, which is one of the angles, you could think of that as elevation, and phi, you could think of that as rotation. So hopefully your mind can handle all that. Then we have some stuff that is really wild. Capital R, capital Y, an M, and a little bitty L, and then a theta and a phi. So here you notice that we've got the R, the theta, and the phi in this expression, and we're going to relate that to those values. Okay, let's look at this capital R function with respect to R. This is the R, this is the radius, and this radial function changes. Now let's see what this thing really is. This carries all the information about the size and the shape of the orbital, and that's really important. The principal quantum number is n, the angular momentum is L, and the effective nuclear charge is Z. So, for instance, and let's break all this down, is 1s is like this form, 2s has a radial node, and 2p grows from 0, then decays. Whoa, what's all that about? Well, have you seen the funny shapes that come from atoms that have all these orbitals filled in? And what we'll do is even talk about hybrid orbitals where things combine into molecules. But the point is that this has all that distance information in it. And also these numbers. Now, what's this all about? This is the spherical harmonic describing the angular or the shape orientation part of the orbital. The radial function depends only on the distance from the nucleus. So as you move from the nucleus, you'll get different values for the radial function. The angular function, this y, Lm, is a function of theta and phi. This gives you the spherical information about the shape and the orientation. Angular momentum is what happens when things spin. The magnetic number is the orientation of the orbital. So think of it this way. This determines the shape, and this determines the orientation. So those magic numbers will tell us all kinds of things. And let's look at the different things. S, P, D, F. Those are the orbitals, and magnetic number determines where the lobes of an orbital point and where the nodes, the zero probability, lie. The angular symmetry. So if we know this information, we can draw a picture of those electron orbitals, which aren't just things that circle the nucleus, but they're shaped into these funny shapes, which you probably have seen in chemistry books. Here's a summary of these items. R, distance from nucleus, theta, polar angle, phi, azimuth angle, radial part, angular part, orbital angular momentum, and magnetic quantum number. Now, to understand each one of these would be really important if you're a physicist, but we're pretending that we're quantum chemists. So if we have all these numbers that we can come up with, then we can draw pretty pictures of the way these things look. Okay, I'm at the marker board. Isn't that interesting? Let's look at this v as a function of r. V as a function of r. And I think we've just went over this, so this should be fresh in your mind. Then we have the full Hamiltonian equation, or actually the full Schrodinger equation, and it's put in slightly different form with this form here that we want to try and figure out. Spherical coordinates. When I was preparing this, the spherical coordinates got really messed up in my mind. Okay, let's do a visualization of this. What I'm going to do is put the z-axis, that's supposed to be a straight line, but this is the z-axis, and I'm going to make this cross the line, the x-axis. If you're only in 2 dimensions, the z-axis would really be the y-axis. But anyway, in 3 dimensions, I'm going to make the y-axis, I'm going to draw it at kind of an angle, but think of it as sticking out of the page. And the spherical coordinates are going to be composed of the r radius and these 2 angles. So we need to describe these 2 angles and get it straightened out in our head. Along the z-axis is going to be r, and if it's all on the z-axis, then that's going to be at a theta angle of, let's see, what would the theta angle be? The theta angle would be coming from the z-axis down here. So the theta at 0 would be up in this direction. So if cosine of theta is 0, then that's going to be 1, and all of the r length is going to be on the z-axis. Now, what if phi is, how come I don't have anything about phi? Because if it's cosine of 0, it's all going to be 1 here, and the phi angle doesn't have any effect on it. Now, the phi angle starts at x and goes this direction. So phi of 0 is right on the x-axis. Phi of pi over 2 is on the y-axis. So the x-axis is going to be r sine of theta. If it's all x, it's going to be all the way down here, and theta is going to be pi over 2. And the phi angle is going to be 0 because it's right up here. If it's all y, it's going to be r sine of phi, and phi is pi over 2, so it's all on the y. And the theta angle is going to be equal to pi over 2. I just fixed this. This was cosine, it should be sine. Because if both of these are pi over 2, then both of these will be 1 over here. The theta will be pi over 2, and the phi will be pi over 2, and that'll be the y-axis when that's true. Previews of coming attractions. First, we'll talk about the geometry of spherical coordinates. And we'll kind of get an intuition for what these things are like. Because before we can come up with the Laplacian, we're going to go through the divergence. And before we can do the divergence, we have to understand spherical coordinates a little bit better than what we have so far. Here's the divergence. And then finally we'll get to the Laplacian. And then we'll get to the Schrodinger equation for hydrogen, and then we'll get to the Schrodinger equation for helium, and then we'll get to Qiskit approximation methods. 1 per video. And look at all these different kinds of basis sets that we can go over. So this is all going to be a video series. So if you're not going to be a quantum chemist, then I've proved it now with this upcoming series.